Hi, in this lecture, I'm going to introduce the equivalent circuit theorems, like the Thevenin's theorem, the Norton's theorem, and also the superposition method to convert a regular linear circuit into a equivalent circuit. So the purpose of this kind of conversion is to simplify the structure of the circuit, so you know what's actually going on in the circuit instead of looking at a really complicated circuit network, but not really sure what's this circuit doing actually. Okay. So first one, the Thevenin's theorem. So the statement or description for the Thevenin's theorem sounds like this. So any linear circuit can be simplified to a structure like follows. Any linear circuit can be simplified to this. Okay, and here is a load resistor. So the load resistor does not have to be a resistor. It can be anything. It's just a load. You can treat this guy as a black box. Anything performed as a load for the entire circuit network. And this is an equivalent, Thevenin's equivalent voltage source. It's called ETH. And this is Thevenin's equivalent resistance. It's called RTH. So based on this, because the load is a load, it's being provided by the customer or the user. So it's not being changed. So whenever you see a complicated circuit network, the purpose or the way to convert it into this equivalent circuit is just to find out ET and RTH. Then you just draw the circuit in this topology. You're getting the equivalent circuit. Okay, that's it. So let's look at example. Example 1. And we have a voltage source, a resistor, another resistor, a current source, and here's a load. Again, the load right here is a load resistor. This is 22 volts, this is 4 ohms, this is 12 ohms, this is 2 amps, this is 1 ohm, and that's entire circuit. So now let's find out ETH and RTH. So I'm going to do RTH first and show you the procedures to get RTH. For RTH, step 1, remove RL. Remove the load. Step 2, short the voltage source or remove the current source. I mean, if you have both voltage source and current source, you need to do both, right? Short the voltage source and disconnect the current source. Short the voltage source and disconnect the current source. Step 3, just calculate RTH. Get RTH. So let's follow this procedure and try to get RTH from this example. See how I'm going to do that. So first, remove RL. So this is gone. It's not in the circuit anymore. And short this guy, disconnect this guy. So eventually, you are going to see something like this. Okay, so the voltage source is shorted and the current source is disconnected, so nothing is here anymore. I just remove it. And then the way to get RTH from this resistor network is to looking backwards. Imagine that you are here looking in that direction. So this is 4 ohms, this is 12 ohms, this is 1 ohm. So find out the equivalent resistance of this resistor network. So that would be RTH. So when you look backward, you are thinking about like there's a current, a little current being injected into the circuit. So you're looking at here, and then you have two branches. So these two resistors will be in parallel, and then come back, merged back to the main network and come back to this node. All right. So it's going to be 1 ohms RTH equals to the 1 ohm resistor in parallel with what? Actually in series with these two resistors in parallel. So it's going to be 4 ohms in parallel with 12 ohms, which equals to 1 plus 4 times 12 over 4 plus 12. So this is 48 over 16. It's going to be 3. So totally it'll be 4 ohms for RTH. So now we find out RTH for this equivalent circuit. What about ETH? So the way or the procedure to find ETH is follows. For ETH, first, for step 1, remove RL. Step 2, ETH is the voltage at the output terminal. It's pretty easy to find. You can use a match current method or a node current method or whatever method you have learned to calculate the voltage at the output terminals. ETH is the voltage at the output terminal. So still the same example here. So now you are not removing the voltage source and current source since both of these guys are contributing the voltage to the output terminal. So you just need to remove it and then find out the voltage here, right? Because this is ground, so the voltage here is actually the voltage being applied to this load resistor. So the circuit looks like this. This is 32 volts, this is ground, 4 ohms, 12 ohms, and 2 amps, and 1 ohm. And you have to remove the load resistor. And so this voltage here will be ETH. Okay. And now let's solve this circuit and try to find ETH from here. All right. We have learned a couple of different circuit analysis methods. So which one you want to use for here? Because the currents are being merged into this node, I think it's fine to use a node current method. Let's try to do it. So this is I1, and this is I3, for example, and this is I2. No, let's assuming like the current going into the terminal is I2 because the current here is going up and flowing to the left. So if you have labeled I1, I2, I3 over here, and the first equation you can write down will be I1 plus I2, which are the two currents getting into the junction, equals to the current flowing out from the junction, which is I3. So the first equation will be I1 plus I2 equals to I3. And the second equation, I2 is flowing here, and here's a 2 amps current, and this is disconnected, right? Nothing is going out here, so no current is going to flow through this direction because it's disconnected. So the 2 amps has nowhere on the right side, so it's the only way to flow is the left side. So 2 amps is going to equal to I2. Okay, pretty simple. And what's the last equation you can list over here? Because you haven't involved this guy into the equation, and you have to use it because it's contributing the voltage to ETH. And now you can see that ETH hasn't been involved as well. ETH is here, there's no current, means no voltage drop. So ETH here as well. And so if you have voltage over here, it's pretty simple. You can get I3. You just use the ETH divided by 12 ohms, you can get I3. And since you know the voltage at these two nodes, so 32 volts minus the ETH, you can get the voltage drop across this 4 ohm resistor. So you can get I1. And I2 is given, so you can just use the voltages to represent I1, I3, and to form the other equation for the node current method, right? So let's do it. So here's ETH because no voltage drop across here, ETH here, ETH here, ETH here. So I1 equals to 32 minus ETH over 4 ohms. So get I1. And I1 plus I2, which is 2 amps, equals to I3. So I3 is ETH over 12 ohms. Okay, so these are the three equations you can use for the calculation. And I mean, this one only has one variable, so you can actually calculate ETH pretty easily. So I will directly calculate. I mean, so how can I simplify this one? Just times 12, right? So times 12 on both sides of the equation. Let's label it. From 3, we can get times 12 on both sides. You're getting 96 minus 3 ETH plus 24 equals to ETH. So eventually ETH equals to, move to here, you're getting 4. It's 120 divided by 4, which is 30 volts. Actually. And so you get ETH from here. Do you really need anything else? Nope, because you already got RTH and you have ETH. So the Thevenin equivalent circuit is this. It's a specific topology, which is RL. Doesn't matter what's RL. ETH is 30 volts and RTH is 4 ohms. All right, that's how you get your Thevenin's equivalent. And now I'm gonna take a pause, and in the next lecture, I'm gonna show you how to do a Norton equivalent circuit conversion. See you in the next lecture.